Okay, we are in Introduction to Statistical Learning, Chapter 11. We are on the final conceptual question, which is question 9. And we have parts A through D here. But all of these have to do with exploring the consequences that survival times follow an exponential distribution. So that's what we'll do. Just a quick comment, if you're not really familiar with some of these probability distributions or ideas of modeling waiting times or times between events, it is a pretty standard assumption to make that when we are measuring either area or time between events or something like that, that we use an exponential distribution. So that's not an arbitrary thing. Okay, so for part A, right here, assuming that survival time follow an exponential distribution, where the density of an exponential distribution is given here, okay, lambda times e to the negative lambda t. So we're going to use relationships provided in exercise 8 to show that the survival time equals e raised to the negative lambda t power. Okay, so the relationship, well, I think we only use one relationship from up there, but we have this as our density function, and the important relationship here is that the cumulative distribution of survival times is the integral from 0 to t of the density function. Okay, and so if we just go through and work all of that out, so we have f of u, because we're going to integrate up to t, right? So it'll become a function of t eventually. But we get our density function. We can take the lambda outside of the integral since it's not a function of u here. Okay, and then when we take that integral, we get this guy right here, and we evaluate it at u equals t and u equals 0, subtract them from one another, and we come out with this guy right here. Okay, well, this is the same. Okay, so this equals the cumulative probability distribution. Well, there's a relationship between the cumulative probability distribution and the survival function, and that is that well, it's exactly this, right? So the cumulative function is 1 minus the survival function, right? And so if we just do the arithmetic, we get that the survival function is this, which is what we were meant to show. Okay. Okay. Now for part B, we suppose that all of our events our n events are independent, okay, and they follow exponential distribution again. And so we're going to write out the likelihood function. Now the problem gives us up here, it gives us a version of the likelihood function. Okay, so we're taking the product over all n observations of the density function to the delta, right, times the survival function 1 minus delta, right? So it's kind of like a binomial. They either survive or they don't, at any given time. So okay, so we just start working with that, and so we expand these two terms here. Okay, well, there's really not much to say other than we expand until we get a function for the likelihood. And then what's important, or another important part about this, is that because this function is often very ugly, we often take the logarithm of it to get the log likelihood. And so if you take the log of this likelihood, you come up with this expression right here. And the reason that that's important is because in part C, we're going to find the maximum likelihood estimator for lambda. And the way that we do that is by taking a derivative of the log likelihood, setting it to 0, and then solving for lambda. And like I was saying, often the log likelihood is much easier to take derivatives of than the raw likelihood. Okay, so we're meant to show that the maximum likelihood estimator for lambda is that expression right there. And so I'll try not to just narrate the math. You can follow the math for yourself. But we take the derivative of the log likelihood with respect to lambda, and that's all that's happening here. And eventually we get an expression that we set to 0 and then just solve for the lambda. And so from this expression, it becomes pretty clear, how we get an expression that's suggested by by the question. We get a solution suggested by the question. So we subtract the yi over, divide by the sum of the deltas, and that gives us 1 over lambda. So if we want lambda, then we just reverse the fractions, right? And so we come out with this guy right here, which is what we were meant to show. Okay. And then finally, for part C, for part D, we use our answer to part C, okay, which was actually technically given to us. Okay. But we're going to use that finding to get a mean estimator for survival times. Okay. Now, one way that we could do this is with expectation operators, right? We could take our we could take the probability of the different values and so on and so forth, and integrate them or sum them. But we don't have to do that, because for an exponential distribution, the random variable, the mean is 1 over lambda, right? And we already found lambda up here, right? So that means that our expected value is 1 over lambda, and we just found an expression for 1 over lambda. It's 1 over the fraction that we just found, and so we can just reverse that. Fraction, and we come out with the sum of the y's divided by the sum of the deltas is our expected value for survival time. Okay, call that good.